Hello and welcome to this session of EduSat. Look at the second unit, which deals with matter waves and the uncertainty principle. So basically our aim in this particular session is to emphasize the dual nature of matter and some of the central concepts of quantum mechanics like the uncertainty principle, and we shall go on to see how these are very real effects and how fundamental they are to the theory. So let's start with how quantum mechanics came about, the birth of quantum mechanics. We've already seen that at the turn of the last century, there were several experimental observations which could not be explained by the established laws of classical physics. And this called for a radically different way of thinking. And by the established laws of classical physics, I mean things that were already known well by then, like Newton's laws and thermodynamics and classical electrodynamics and so on and so forth. So there was a need to look at these observations in a completely new light, and this led to the development of quantum mechanics, which today has graduated to become the fundamental theory of nature. Now you might wonder how quantum mechanics relates to you and me. Well, you must have heard that quantum mechanics seems to apply to subatomic or microscopic particles, but remember that macroscopic objects and the things around us and you and me are also finally made up of smaller entities or microscopic particles. And hence, if quantum mechanics is the theory of the microscopic world, it is also the theory of the macroscopic world, and hence it's not wrong to say that it is the fundamental theory of nature. Let me refresh your memory about what were these key events and observations that led to the development of quantum mechanics. We have already seen that the birth of quantum mechanics was heralded by a discovery, or rather the hypothesis of Planck. So this was in 1901, and that is often regarded as the magic date, as the time when quantum mechanics was born. So you can see that we've already crossed 100 years with the theory. We've learned in detail about the black body radiation spectrum. Stated simply, the black body radiation spectrum simply refers to the kind of radiation that a hot body would emit. And you have seen this in your daily experience, that whenever you heat up an object to really high temperatures, for instance a chunk of iron, then it glows. It not only emits visible radiation, which we can see with our eyes, but it also emits thermal radiation. So we are talking about radiation which the body emits by virtue of its temperature. We've also seen a very characteristic behavior, in the sense that as you increase the temperature, the radiation that you see, if I'm talking about visible radiation, seems to change in, let me say, color. So something can glow red hot, it can glow blue hot or white hot, and so on. And we see this all around us. It's a very commonplace experience. And if you've looked at the night sky and you look at the stars, you would know that the stars which are red are cooler, which look red to you are cooler than the stars that look blue. So such a commonplace experience as a black body radiation spectrum could not be explained by what we knew around the time that Planck gave his hypothesis, that is classical mechanics, thermodynamics, and so on. So it took Planck a very courageous and radical new hypothesis like quantization, or the fact that energy can be exchanged only in quanta and not otherwise. So he had to put forth this radical hypothesis in order to explain the black body radiation spectrum, and we've all seen it in the previous presentation that E is equal to NH nu was this revolutionary idea that Planck brought about. The second thing that you've looked at before was the photoelectric effect. Now we all know what that is. Whenever there is light on certain materials, if light falls on certain materials, the material ejects electrons, and this is called the photoelectric effect. And we have seen previously that it is impossible to explain the intricacies of this effect, especially some of the observations, in terms of the already known classical theories. For instance, this was discussed by Dr. Lamba, that things like there is no time lag, there is an instantaneous emission of electrons, and also the way the frequency of the incident light and the intensity of the incident light affects the emitted electrons. Now these are things which could not be explained by the established classical theories and needed a quantum mechanical explanation, and we all know that this was provided very successfully by Einstein. So that was in 1905. There were many other observations, and I'm only referring to some of them. You have the model of the atom, which was also explained to you in great detail, which Rutherford had first discovered. Then the fact that spectral lines are discrete, the quantum theory of spectra, which also we looked at in great detail. This was due to Bohr. Going on, we had the scattering of photons of electrons, which was the Compton effect, discovered by Compton in 1922, which again could not be explained in terms of classical mechanics. First of all, even the concept of a photon could not be explained within classical mechanics. So these are detailing some of the events and observations in the history of the birth and development of quantum mechanics. And then you had things like the Pauli exclusion principle, which you might have come across. And then there was the hypothesis of Louis de Broglie about the wave nature of matter, and the experimental test of matter waves, which was essentially validation or verification of the hypothesis of de Broglie. So these were some of the key events which I've sort of listed out year-wise, starting from Planck's discovery in 1901 down to 1927, which were very, very major, you can say, milestones in the development of quantum mechanics, and sort of it re-emphasized the great role that this theory plays in explaining nature. Okay, just have a look at some of the people who were associated with these discoveries. You've seen these photographs before. That's Planck, Einstein, Rutherford, Bohr, and Compton. That's Pauli, de Broglie, and Davison and Germer, who finally tested the hypothesis of de Broglie in real experiments involving electrons. So this is like some kind of a history of all what happened, which led to the birth of quantum mechanics. Now, one of the things that is often spoken of when you talk about the origins of quantum mechanics is the nature of light. Now, we have always wondered about light for millions of years, well, thousands of years, that what is light? Is it a wave? Is it a particle? What is it comprised of? And this wondering about the nature of light, eventually led to ideas which sort of culminated in the birth of quantum mechanics. So let's look at this slide. The birth of quantum mechanics is intimately linked with theories and discoveries relating to the nature of light. So the question that everybody asked for many years is, what is light? Is it a wave or a particle? And we have references to this question in the previous presentation also. So what is light? Is it a wave or a particle? what kind of answers came for a question like that? So let's look at the story of light. So if we go back, really back in time, we go back to Newton, and we can credit him with the first theory of light, and this went by the name of the corpuscular theory of light. So Newton essentially said that light comprises of particles. Now he did not say what these particles are, he did not know what these particles are, but he just thought that a source emitting light is essentially emitting a stream of particles, and this theory was fairly successful in the sense that it could explain things that we observe every day about light, like the rectilinear propagation of light, the fact that light travels in a straight line, and it could explain a few more things, and it was a successful theory and fairly satisfactory to Newton, and it remained the prevailing theory for many years. But sometime later, Huygens, in fact not even very much later, but during the time of Newton itself, Huygens came up with a theory which said that no, light is not a stream of particles, it is actually a wave. Now, such was the power of Newton that people did not take much notice of what Huygens was saying about the theory of light, but it nevertheless remained a very new concept, that it is a wave. Next up in the story of the discussion on what the nature of light could be was the double slit experiment of Thomas Young. Now this is something that you are all familiar with. You all do it in school, and there are signatures of interference of light everywhere around us. But this was first shown by Thomas Young, and we know that interference, diffraction and such phenomena are always associated with waves, and you've seen it in water waves, in sound waves. And what Thomas Young demonstrated was that this actually exists for light too. So this was a spectacular event in some sense, because it really proved beyond doubt that light had all the makings of a wave. And incidentally, Young was not a physicist, he was a physician who was interested in sensory perceptions of light, and it got him interested in all these experiments. So following Young, there were greater developments, and there was Maxwell, who established that light is an electromagnetic wave. You must be all familiar with Maxwell's equations. Maxwell's equations are equations which relate electric and magnetic fields, and one special property of these equations is that they have a solution which is a wave. And it turned out, and these are electromagnetic waves, and it turned out that the speed of these electromagnetic waves that Maxwell was talking about was the same as the speed of light. So it left very little doubt that light was indeed a wave. Not only was it a wave, it was an electromagnetic wave. Okay, so what is an electromagnetic wave? I guess you are all familiar with it. It relates to the oscillations of electric and magnetic fields. So by the time of Maxwell, it was firmly established that there was enough evidence and proof that light was a wave, a transverse wave, an electromagnetic wave. Now, was that the end of the story? No, because following Maxwell came the photoelectric effect, and we have just seen in the previous presentation that the photoelectric effect in all its glory cannot be explained without the notion of the quanta, that is the packets of light, the photons. So once again, and this was due to Einstein, so once again the story of light sort of was flipped around, and coming from the particle picture of Newton, you came back to a picture where you again said that light was made of particles. It better be made of particles, otherwise I cannot explain the photoelectric effects. But now we are wiser. We know that these are not just some particles, these are photons. And then later on, there were more establishment of this fact. There were more experiments which nailed this fact even further. And we've seen the Compton effect. And what happens in the Compton effect is that photons. So it's very well to say that photons are particles of light, but do they behave like particles? I can say they may be quanta of light, but they may not necessarily be particles. And the Compton effect sort of established that the photons behave just like the particles that we know of. For instance, two billiard balls colliding and how they would scatter off each other, an elastic scattering. A similar kind of effect happens if photons collide with electrons. So Compton effects show that photons are scattered off electrons in a similar way as particles, for instance, two billiard balls could. So once again, compelling evidence for the particle nature of light. So what is it? Is it a wave or is it a particle? Well, before we go on to this, a quick look at this slide, which shows all the people associated with the story of light: Newton, Huygens, Thomas Young, Maxwell, and of course Einstein, who's there everywhere, and Compton. So, what's the answer to the question, what is the nature of light? Well, we say light has a dual nature. It is both a particle and a wave. It is a wave, it is an electromagnetic wave, and this is easily seen in experiments of interference, diffraction. There could be others like polarization and so on. And we cannot negate the fact that it is a particle, because we have very strong proof of that, and these are photons, and this particle nature of light shows up in the photoelectric effect, the Compton effect, and many other places. So by now we accept the fact that light has a dual nature. So this is the wave-particle duality for light. Now let's ask another question. What about matter? Light has a dual nature. We are fairly convinced, and we accept it happily, that it has both a particle nature and a wave nature. At that time, people ask the question, what about matter? Now, why would you ask a question like that? Well, the reason is, as was also referred to in the previous presentation, that nature loves symmetry. And physics is driven by this notion of symmetry. We've seen it in other fields and areas. For example, electromagnetism. All of you have learnt in school that a changing electric field causes a magnetic field. So one might naturally ask, by symmetry, does a changing magnetic field produce an electric field? And the answer is yes. So whenever one thinks in terms of symmetry, chances are that we stumble on the right answer. So it was natural to think that if light could be both wave and particle, what about matter? So let us phrase it this way. If light, which was traditionally understood as a wave, also turns out to have a particle nature, might matter, which is traditionally understood as particles, also have a wave nature? And the answer is a resounding yes. And this was what you heard before also. This was the hypothesis of Louis de Broglie. De Broglie proposed that not only does radiation, that is light, have a dual nature, matter also has a dual nature. And not only did he suggest this, he also went ahead and gave us an expression for what would be the wavelength of a particle. So a particle with a momentum p has a matter wave, and he called these waves which were associated with matter as matter waves. So a particle with momentum p would have a matter wave associated with it, whose wavelength is given by h by p. Now h is the all familiar Planck's constant, which you have seen before in the case of photons. So let's see again, the connecting link is Planck's constant. So the link between the wave and the particle nature of matter and radiation is the Planck's constant. You can see here, when I say light, I mean radiation, which is not just visible light that you and I can see, but the whole range of electromagnetic radiation. And here we know it is a wave, but this expression here also tells you that it is quantized in packets of h nu. H is Planck's constant, E is the energy. And just now we've also seen that matter, which is a particle, can also have a wave associated with it, and the wavelength of this wave is given by lambda, and lambda is related to the momentum of the particle, and again the connecting link is Planck's constant. Now the question to ask is, why isn't the wave nature of matter more apparent to us? It's very well to say that all of matter has a wave associated with it, but why is it that I cannot see the wave associated with a classical particle like a stone or a ball or a car and so on? And we've already got answers to this question, and the answer is, have a look at the value of the Planck's constant. It is so very small, 6.6 into 10 raised to power minus 34 joule seconds. The answer to the question as to why the wave nature of matter is not more apparent to us is that Planck's constant is so small that we don't observe the wave behavior of ordinary objects. For their de Broglie wavelengths could be many orders of magnitude smaller than the size of a nucleus. So if the de Broglie wavelength associated with you and I is smaller than the size of a nucleus, it's obvious that I'll have absolutely no feeling of the wave nature of familiar particles in the macroscopic world. Okay, so now what are we trying to say? We say that matter is both particle and wave, and we want to link these two concepts. So is it possible? How is it possible for something to be both a particle and a wave? Now, before we see how the two concepts can get linked, let us just again remind ourselves, what is it that a particle means to us and what does a wave mean to us? So if I asked you what a particle is, then our traditional understanding of a particle would be that it is something, for instance, like this, which is localized. Okay, so think of this as either a dust particle or a ball or a stone or whatever. But we all agree that anything that we call a particle is localized. It has a definite position, and if it's moving, it has a definite momentum, and it is confined in space. I know that this is the particle and it's going to remain in this spatial area. Even when it moves, its spatial extent is confined. So that is a particle. What is a wave? Our traditional understanding of a wave is something like this. We are all familiar with wave notion. Now, the wave really is an opposite of what we would imagine a particle is. It is something that is completely delocalized in space. Okay, it is spread out in space, and it can move and pass through objects and so on. So a wave is something which is completely spread out in space. A particle is something that is localized in space. So how do we link up the two? How can a particle be a wave? How do we associate a wave nature to a particle? Well, what could represent both wave and particle? Well, one has to think of a description of a particle which is consistent with our notion of both particles and waves. That is, I want a description which is mathematically sound and which is such that it fits in with my understanding of a wave. For example, it satisfies an equation that a wave would follow. Also, it better be localized in space, because otherwise it does not fit into my description of what is a particle. Is there such a description? And the answer is indeed yes. We describe a localized particle, we give it a wave description in terms of something which is called a wave packet. Now this is a wave, but it is also localized in space and time. You can see that something like this could explain a particle, because it's not something that is spreading out into space infinitely in both directions. So if I had something like this, then this would be a wave, because indeed it is constructed like a wave, but it would also be a particle if the spatial extent of this wave packet is compatible with the localization of the particle. So if I had a wave packet, I can buy the idea of a particle being a wave. How do you construct a wave packet? Before we do that, let's go back to something that we've learned in high school. That is, what happens when you add up waves? We are all familiar with the superposition principle. You all know that this holds for all waves, whether it's sound waves, water waves, light waves, etc. In fact, the Young's double slit experiment is a classic example of interference fringes formed when two waves interfere with each other. So the superposition principle, as you all know, simply states that if you have two or more waves in an area, then the resultant amplitude due to these waves is the sum of the amplitudes due to each of these. So this is a very small example which shows it. You see the waves in blue and green. If they are together in the same region, then if you apply the superposition principle, they interfere in such a way that the resultant wave is this big red wave. So the amplitudes have added up. Now this is a really simple example in which both the green and the blue waves have similar frequencies and phases and so on. So it very neat addition. If they were totally out of phase, that is, if the crest of the blue and the trough of the green coincided with each other, then I would have almost zero in the resultant. So this is the superposition principle that everyone is familiar with. So why am I talking about the superposition principle right now? Because I want to find ways of constructing a wave packet, and I want to use the superposition principle to do so. So I've seen now how two waves add up, and it was a very simple example of two waves with the same frequency, nearly similar waves, very small difference in amplitude. Now what happens if I had two waves with slightly different frequencies? Let's have a look at how they would add up. If you had two waves, this, and they had slightly different frequencies, then when they add up, this is how the resultant is going to look. Now you can see this is very different from the red wave that we saw earlier. So this is just two waves, but if you remember that this is what I want to get, a localized wave packet, then from this clue I could think of adding up not just two waves but many waves of varying frequencies. And when I do that, if several waves of different wavelengths or frequencies and phases are superposed together, one would get a resultant which is a localized wave packet. So instead of just adding two waves with slightly different frequencies, if I could add up, say, hundreds of waves together and their frequencies slightly varying from each other, I would end up with a resultant which looks like a wave packet. So that's a neat way of getting a wave packet, and a wave packet describes a particle, because a wave packet is something that fits in with both my description of what is a wave and what is a particle. It is a wave because it's constructed of waves. It would obey all the properties that a wave would. At the same time, its spatial extent is small, and it's not extending to infinity in all directions, and so a wave packet also describes a localized particle. So here I say a wave packet is a group of waves with slightly different wavelengths interfering with one another in a way that the amplitude of the group that is the envelope that you saw, is non-zero only in the neighborhood of the particle. Okay, and everywhere else, if you go far away from the wave packet, the amplitude goes to 0, meaning there is nothing there. So that is like a particle. A wave packet is localized, and so it is a good representation for a particle. Okay, now a wave packet has certain properties associated with it, and as I said before, a wave packet is constructed by adding up several different waves and tons of waves. So you will have a range of wavelengths or frequencies, and there would be waves corresponding to each one of them, and they would all add up to give you the wave packet. The spread of the wave packet in wavelength depends on the required degree of localization in space, and the central wavelength is given by the de Broglie relation, that is lambda is equal to h by p, where p is the momentum of the particle whose wave packet or whose wave nature I am describing. What does this mean? The spread of the wave packet in wavelength depends on the required degree of localization in space. This simply means that the wave packet, if you need a narrow, you have to choose the waves that you add up depending upon how narrow you want your wave packet to be. So if I want a highly localized wave packet, I would need to add up many waves of varying frequency. So I would have or varying wavelength. So I would have a large spread in wavelength. So the wavelengths would range from one end to the other, and there would be a large spread in the wavelength. But if I didn't want a very highly localized wave packet, then I would have a smaller range of wavelengths to choose from. A good question to ask is, what is the velocity of the wave packet? If I want it to be a fitting description of the particle, then the velocity of the wave packet should be the velocity with which the particle is moving. And indeed that is so, as we can see. In the context of the wave packet, we talk of phase velocity and group velocity. The velocities of the individual waves which superpose to produce the wave packet representing the particle are different. The wave packet as a whole has a different velocity from the waves that comprise it. So phase velocity is something that is defined for a wave packet. It is the rate at which the phase of the wave propagates in space. And then there is something called a group velocity, which is the rate at which the envelope of the wave propagates. So we are not calculating these, but I'll give you the expression for phase velocity. Let me call it Vp is c square by v, where c is the velocity of light, the speed of light, and the group velocity Vg is v, where v is the velocity of the particle. So really the entire group of waves, the envelope of the group of waves is traveling with a speed which is equal to the speed of the particle itself. Okay. Next, let's move on to another very important and central concept of quantum mechanics, and that is Heisenberg's uncertainty principle. Now, this is something new, but it's very central to the quantum framework. The uncertainty principle is an important consequence of the wave-particle duality of matter and radiation and is inherent to the quantum description of nature. Simply stated, and this is a very simple statement of the uncertainty principle, that it is impossible to know both the exact position and the exact momentum of an object simultaneously. Now remember, the uncertainty principle is a fact of nature. Sometimes there is a misconception that the uncertainty comes out only because of the experiments that we do, and that our experiments are not good enough, and if we had really strong experiments, we would not have uncertainty, but that is not true. Uncertainty principle is very basic to the quantum nature of things. It is inherent and it will never go away. So how do we state it more mathematically? So if I'm trying to associate position and momentum with a certain particle, there is a certain uncertainty in its position, let me call it delta x, and an uncertainty in its momentum, let me call it delta px, then the uncertainty principle gives you a lower bound on what this product can be. So delta x, delta px has to be greater than or equal to h by 2 pi. So this product can be never less than h by 2 pi. So if I have a very small uncertainty in position, I will have a very large uncertainty in momentum, and so on. Now one must know that Heisenberg's uncertainty principle is something which is inherent in quantum mechanics and exists in every field, I mean wherever you're talking about any system, and in particular it applies to all conjugate variables. This is something that you will learn about later. So we've already seen the position, momentum, uncertainty. There is also an energy time uncertainty where energy and time are conjugate variables. Now we just discussed the wave packet, and it is interesting to see that the uncertainty principle is also linked up with the notion of the wave packet. So this is my statement of the uncertainty principle. This is the de Broglie relationship for the wavelength. Now if I had a spread in the wavelengths, that would translate to a spread in the momenta, because wavelength and momenta are related in this fashion. So as I told you before, that if I need to construct a narrow wave packet, I need a large spread in wavelengths. I need tons of different wavelengths over a big range, which means I need a large spread in momentum. So according to the uncertainty principle, a large spread in momentum should mean a small spread in position. Or in other words, large uncertainties in momentum means small uncertainties in position, means more localization. So see here, a wave packet like this is more localized. It is constructed of a big range of wavelengths, which means it has a large spread of momenta. Whereas a wave packet like this, which is spreading out in space, it's almost like a single wave, has almost a certain momentum, but there is a delocalization. It has a large spread in position. So you can see that the wave packet is a classic example of uncertainty principle in action. The uncertainty principle is not just a theoretical statement. It has some amazing consequences, and I'll just quickly list them. One consequence of the uncertainty principle is that the path of a particle, what we call a trajectory, is not well defined in quantum mechanics. Now what does that mean? For instance, what is a trajectory? If you were to sort of throw a cricket ball up in the air and you notice the parabolic curve that it takes, it simply means that at every point you know what its position is, what its momentum is. But I just said that position and momentum are uncertain in quantum mechanics, and there is a minimum limit beyond which you cannot get more exact. So in quantum mechanics you can never know simultaneously both the position and the momentum exactly. So which is a way of saying you can never have a well-defined path or a trajectory. Another consequence of the uncertainty principle is that electrons cannot exist inside a nucleus, and also the fact that atomic oscillators possess a certain amount of energy known as the 0-point energy even at absolute zero. Now we know from the classical theories like kinetic theory and so on that if temperature drops to absolute zero, the motion of all the oscillators are going to freeze and they should have zero energy. But the uncertainty principle just told me that the position can, the uncertainty in position can never be zero. So a consequence of this is that nothing can have zero energy even at absolute zero. There's always something called a 0-point energy associated with oscillators. Okay. Why isn't the uncertainty principle more apparent in our ordinary experience? Well, you should have guessed by now that it's Planck's constant once again. It is so small that the uncertainties implied by the principle are also too small to be observed. They are only significant in the domain of microscopic systems. So the uncertainty in the position of a stone or a ball or you and I is so small that it's really insignificant because of the nature of the value of Planck's constant. So although inherent to the quantum nature of everything, and that is something that you can never do without, at the scale of macroscopic objects in the familiar world around us, the uncertainty principle really is not of much consequence because we don't experience it because of its magnitude being so small. Okay, so let us summarize what we have spoken about so far. We have seen that matter and radiation have a dual nature of both particle and wave. The matter wave associated with a particle has a d Broglie wavelength given by h by p. We've also seen that if we wish to link the two, particle and wave nature, we need a localized description of a wave. A particle can be represented then by a group of waves which is called a wave packet. The group velocity of the wave packet is v, if v is the velocity with which the particle is moving, and the phase velocity of the wave packet is c square by v, which is the velocity with which the phases are moving. We've also gone on and seen or heard about the uncertainty principle, which is very inherent to quantum mechanics, and it is an important consequence of the wave-particle duality of matter and radiation. And this is inherent to the quantum description of nature. It applies to all conjugate variables and also to the notion of the wave packet, which we've already seen. Okay, so let me ask the question. So that's all this is all very nice and all the mathematical statements, but are matter waves for real? And we've already seen that indeed, after de Broglie postulated it, Davison and Germain in 1927 electrons can differ and they act like waves. And you should know that this is not just an intellectual curiosity, but something which has big application, and one of the greatest application of wave nature of matter and the wave nature of electrons especially is the electron microscope, which is known to have a resolving power which is much higher than the and I show you examples. Red blood cells, a picture in an electron microscope. This is here, the microscope C. The Japanese experiment with electrons was done in 1989 in Japan, and this is set up for electrons go and go for double slit arrangement and show interference fringes. This is a real data, and here you go. These are the dark and bright fringes which electrons show. And finally, today, advances in technology led to matter wave interference demonstrated successfully not only with electrons but also muons, atoms, and small molecules. In fact, you would be surprised to know that the largest molecule shows interference, and the signature of matter waves is almost 100 atoms. Buckyballs, the molecules which have 60 carbon atoms each, they have shown interference experiment. It's tested at Vienna a few years ago. And bimolecules like this molecule here shows, and this is real experimental data which shows the experimental fringes. This is very recent. And finally, I think we don't need any more proof for the reality of matter waves. What next? One could have matter wave interference experiments for a virus. It's not a remote possibility. So matter waves are real, and we accept that they are real and they are here to stay. If there is a wave, there must be a wave equation. And in your next lesson, in Introduction to Quantum Mechanics, you will learn about the big pillar of quantum mechanics, that is the Schrödinger equation, which describes the nature of waves. So with that, we end this session here, and next time you will be exposed to the Schrödinger equation and what it governs, and that is essentially going to tell you about the wave nature of matter. We have seen enough proof of matter being a wave. Now, how does this wave behave? What are its dynamics, etc. will be something that will be demonstrated by the Schrödinger equation. So, thank you.